Okay, so I asked you last time to finish up that problem, right? So please, if you have that, you can turn that in. And then what I'm going to do is I'm going to pass around a packet of work that I have from you. So please go through this and just grab things out of here. Just make sure you go through the whole stack because you might have more than just one thing in there. And then once you're done with it, please make sure you pass the stack around so it gets around to everybody.
So where do we go and set this up?
Yeah, I'll take that. Anyone else want to turn in today's? Thank you. Okay. All right, so we have an exam on Thursday, right? And that exam will be covering pretty much everything since the last exam. So let's talk a little bit about what's going to be on the exam. All right, and then we'll talk more about it at the end of class because I do want to talk about 5.6 today. But you're going to have on exam 2, which is Thursday, it's going to cover 4.3, so quadratic functions. Specifically, I'm going to give you quadratic functions either in standard form or in expanded form, and you need to be able to graph those. And so when we graph quadratic functions, standard, you need to be looking at these two forms back in your notes. Because how you graph those is a little different, right? Standard, you do things a certain way, and expanded is a little bit different. But both of those, we are always looking for the same sorts of things, like does it open up or down? Right? Does it have a vertex? Well, it should, right? Does it have any x-intercepts? How about the y-intercept? The sketch. Right? These are the things I'll be looking for. So there's more detail in a quadratic function being graphed than there is in a polynomial function. You know, in polynomials, we just kind of up, down, left, right behavior.
And it kind of does this thing.
And then in the middle, we don't really know how high it goes. With the quadratic, we want to actually get a pretty good picture of what's going on. We know exactly how high it goes or how low because we know the vertex. So remember, there was a shortcut formula for the vertex. Remember that? Okay. All right, so quadratic functions. 4.5, quadratic inequalities. Now, I actually did not go through this section in detail because when we got to 5.4, it was called polynomial inequalities and rational inequalities. And we know that every quadratic is a polynomial, right? So the way that you would do a quadratic inequality is exactly the same way that you would do a polynomial inequality. And if you'd like, towards the end of class, I'll do one of these. All right? So that you can see a quadratic inequality being done. All right? You need to know how to do 5-1. So it's actually more than 5-1. It's a couple of sections. 5-1, R4, R6, 5. Yeah, 5 right there. Just that right there. 5-1, R4, R6. This is polynomial functions. Okay, so poly functions. You need to be able to sketch it, right? Sketch a polynomial function. And to do that, what do we need to do a polynomial function? Okay, is it a polynomial left and right behavior? And that came off of that table, right? How many different ways can a polynomial? 4, right? This was this thing, right? That thing. So you got to be able to determine left and right behavior. That you get from the degree and the leading coefficient. You then find the x-intercepts, right? And within that, don't you also look at multiplicities, which is going to tell you whether or not you're going to cross through or if you're going to touch, right? So x-intercepts, I'm going to say with multiplicity. And when we find x-intercepts, didn't that really break down for us? We had to factor the polynomial, right? Within that factoring, right? Cross or what? Yeah, this is going to tell you cross or touch.
Because I was like, I know that's the actual, what do you call that, the word for it.
So when we're trying to find the x-intercepts, we have to set the function equal to 0 and factor. And I can guarantee you that on the test, I'm going to give you something that's not going to factor unless you use the synthetic division with the list of numbers. That's called the rational zero test. I can promise you that. So that's where I'm going to knock out these two sections. I may also give you just its own problem, a long division problem, just by itself. You know, here's long division that you can't use synthetic division on. So just to make sure you understand how to set up the long division and do it. The other thing you have to be able to do on this test is 5.2 to 5.3. And this is basically graphing rational functions. And boy, there was a bunch of stuff we had to do for rational functions, right? Do you remember what some of the things were?
Find the x-intercept.
Okay, find the x-intercepts, find the vertical and horizontal asymptotes, right? Test points. I'm just reminding you of all the things you had to do, right? These are the types of things. And then you draw this picture and you make sure that you're paying attention to where things go, and right? And then 5.4 is the polynomial and rational inequalities. So I've already said that's going to be on the test, right? 5.4. Okay. Any questions? I'll try and show you some specific examples later at the end of class, but
So what we're learning today was?
not really. Maybe as a bonus. Today's information on the test, I'm saying no, maybe as a bonus, all right? But try not to turn off your brain completely, all right? All right, that's pretty much it. So here's what we're going to do today. I'm going to look at 5.6, go through it briefly. I'm going to go back to quadratic functions. There was one thing that I skipped over at the end. Okay, I skipped the end because we ran out of time. We had to take a test. So There's one more thing at quadratic functions I wanted to show you. It was an application. And then after that, we will actually maybe go look at some of my old tests. All right? Sound like a plan? So today, 3 things. 5, 6, revisit quadratic functions, go back and look at tests. Now 5, 6, I'm going to go through pretty quick, okay? And I'll try and explain why I do not like to emphasize this section too much. 5, 6 is titled Complex Zeros. And the fundamental theorem of algebra. All right, so let me start by giving you a function. All right, let me start by giving you a function, then we'll get into all this. Let's say I give you a function f of x equals x squared plus 4. Now we should recognize that as being a quadratic function, right? If I asked you to graph this, you could go through all the different things. You go and you try and find the vertex and all that junk, right? Or you could go back to your toolbox of functions, and we all know that this actually just looks like a parabola, right? X squared, but up 4. So 1, 2, 3, 4. And it opens up like this, and we know that, right? So my question to you is, if it does that, then is it possible for me to break it down into 2 factors? Since it's squared, right? Like if this was minus 4, I could do plus 2 minus 2. But if it's plus 4, can it factor into 2 pieces? No, right? Because there's no x-intercepts, it makes sense that this wouldn't happen, right? Okay, what the fundamental theorem of algebra says is that if you have a function that has a power of 2, in this case 2, but this works for 3, 4, 5, 6, doesn't matter. If you have a polynomial function, it is guaranteed to be able to be factored into this many factors. So if there's a 2 up there, it's guaranteed to be able to be broken down into 2 factors. And you might be saying, wait a minute, we just said it didn't, right? The asterisk next to all this, okay? The big asterisk next to it, this fundamental theorem of algebra, is that you must be willing to allow for complex numbers. If you're going to allow complex numbers to play with us here, then this is guaranteed to happen. You will guarantee be able to break it down. So we have to first understand what's a complex number. So what is a complex number? What have you all heard about complex numbers? What do you know about them? Anybody?
They're complicated.
They're complicated. They're very complex. Anything else?
They fall on a number line at some point.
Okay, so they're in a number line. Are they on our number line?
I thought they were imaginary.
Probably not like an exact.
Imaginary? We've heard of imaginary numbers before, right? We may have talked a little bit about imaginary numbers. Imaginary numbers involve this letter I, right? In fact, I'll revisit this. I'm going to come back to this, but my intention was to at least motivate the idea that the fundamental theorem of algebra says I can factor that, but I have to be willing to allow complex numbers. So let's make sure we understand complex numbers. If you look at the square root of 4, we all say the answer is 2, right?
Plus or minus.
Not if I don't. If you have an equation and you come in and you take the square root on both sides, then it's plus or minus. But if I just write down the square root of 4 right here, it's understood to be called what's called the principal root, which is the positive answer only. Okay, so the square root of 4 is 2. Agreed? If I write this, that's negative 2, right? But what if I write this? So that's where we get the complex numbers from. here, when we say square root of 4 is 2, we're saying what number times itself, right, gives you 4? 2 times 2 gives you 4. This right here, we can ignore the negative, and it's the same question. What number times itself gives you 4? 2, but then make it negative, right? Here, we're saying what number times itself gives you negative 4? And it doesn't make a whole lot of sense.
Yeah, the I thing.
Yes, so this is where we get the I from. We define, so this is a question. We define, so we are coming in and we are defining this. We define I to be equal to the square root of negative 1. I is this thing that when you square it, you get a negative 1. So that means that I squared equals negative 1. That's what it means. Now, if I go back to this square root of negative 4, what I can do is I can break that up into 4 times negative 1, right? That's the same as negative 4, right? And then I can break this into 2 roots because you're allowed to split a root apart. If there's multiplication inside, you can do this. And the square root of 4 by itself is 2. And the square root of negative 1 is I. So the answer is 2i. But you have to not believe it. You just have to understand that we are defining this way. And I think a lot of people, even mathematicians in the very beginning when this first came about, they were very skeptical about whether or not this even made sense to do this, but it turns out later on that it works. Okay, and this is a very good thing to have the I. So, see, I always ride the fence on this. I don't know how deep to go into this. I don't like this section in a college algebra class. Okay, I don't, and here's why. The complex numbers are an extremely difficult topic to go through. In fact, the next time in a math class you would see them, okay, would be you take calculus. Well, you have to go from here pre-cal, cal 1, cal 2, cal 3. Okay, then you can do, after you get through cal 3, then you're free to start taking math electives. Okay, everything in math is pretty much one class followed by the next until you get to cal 3. After cal 3 and linear algebra, after those 2 courses, you pretty much have these different paths you can go down. And one course you can take is called complex variables. And that's where you go back and finally revisit this idea of I. So for me, I don't like it here because all we do is just real quick, just open the window, tell you look in real quick, and then we're going to close it and you're not going to see it for a long, long time. All right? So my opinion is kind of like, why even really try and show you something now?
That's exactly what I was going to say. I was like, if you're not going to really...
Yes.
And, I can understand, yeah, it's a fundamental thing, but if you're not really going to go in depth as to,
I agree. That's why I'm saying this. I don't like it here, but it's part of our curriculum, and I don't want you to come out here with no idea what I is, all right? So let me try and help you understand maybe why it is that you have to wait so long, okay? How about I try and explain to you why you have to wait? Okay. So if you can all please take on faith for now that we are defining the square root of negative 1 to be I, then I'd like to draw you what we call the real number line. Now I'm going to label this double struck R. You've seen this before. And that's just all the numbers we've known our entire lives. And we've talked about this line before. We talked about, hey, at first we started with 1, 2, 3, 4, 5. Then we added 0 later. Then we did the negatives. Then we did the rational numbers, which were all the fractions. Then we did the irrationals. Remember that conversation we had? I remember it, but I was talking, so maybe that's why I remember it. And somebody even asked me, is there a symbol for the irrationals? Who asked me that?
We did.
Okay, I looked into it to make sure I wasn't missing something. There's not technically what you do is you go, that's all the numbers, right? And you take out these. So these were what? the fractions, right? Those are all the fractions. If you take r and you remove all the fractions off this line, if you take every fraction out, then the only thing left in there is the irrationals. So that's them. It's r take away q. Sometimes you can write r minus q, actually, and it's accepted. So r take away q. OK, so this is the real number line. It has all the fractions, all the irrational numbers, pi, e, they're all in there, right? Is I here? No, it's not. I does not live on this number line. So to somehow get some idea of how we could represent I, what we do is we switch from the standard r, which is our real number line, to what we call double struct C, which stands for the complex numbers. And for me to help you see these, what I'm going to do is I'm going to draw two axes. This axis right here, this line, is r. Okay? So that's that number line right there. But now I have this new number line that goes vertically, and this is called my imaginary axis. Okay? That's my imaginary axis. So if I go here, that's 1, this is 2, right? This is -1, this is -2, this is 1, this is 2, right? Got it? So if I want to show you the number 4, okay, let me show you the number 4. Here's a number 4. On this number line, 1, 2, 3, 4, it's right there, isn't it? In the complex number is 4 in here. 1, 2, 3, 4. Yep, it's right there. See? It's here too, right? It's here, there, and it's here also. Now let's look at I. We said I is not here, right? Now I want you to look at this as being one I. Just one I. One I would be, this is the imaginary axis. So one I is right there. It's one unit in the direction of I. You follow this? Kind of, yes?
Why would it not be over 1?
That's a good question. So let me write something else down. How about 1 plus I? So now what we have is something else. This right here, 1, is a real number, right? And we're adding to it an imaginary number. Where would that be? So what part of that is the real part? The real part is the 1, right? So it means I go over 1 and then up I, which would put me here. Do you see that that's 1 plus I? Do y'all see how that works? Yeah? There's nothing crazy or special about this. Do you see it though? Okay, so what about this one? How about -2 minus 3i?
So that would be just over 2.
Over 2,
And then up. No, down.
down 1, 2, 3. Okay, very good. There it is. Yes?
The complex number line just represents I.
Pardon me?
The complex number line, the vertical line, it just represents I.
That's right. It's how many of the i's you have. Okay? So in general, a complex number looks like this. A complex number must look like this. A plus bi, where A is what we call the real part, and B is what we call the imaginary part. Okay? So let's go back and look at this number 4. What's the real part of 4? So 4? What's the imaginary part of 4? So does this number have an imaginary part to it?
No.
It does and doesn't.
I guess it'd be 0 I.
That's right, exactly. This is 4 plus 0i. Perfect.
You can assume, just like with the other thing, there's always a 1 in there.
That's right. There's always one there. So if you're missing the imaginary part, it's actually a 0 in front of the I. Did y'all see that?
So you just have to imagine that it's there.
You just have to imagine that the imaginary part's there, but it's zeroed out. Yeah? But this is pretty profound, because what this is saying is that every number that you've ever done, like worked with in your entire life, is a complex number.
How do you apply
4 is a complex number, right? 4 lives on here. Pi lives on here. -3 lives in here. All the numbers that you normally deal with live here, right? But then you have this additional huge set of numbers that involve imaginaries, yes? I'll get to your question in a second. All right. So far, is this okay? I mean, like, you kind of get the idea of like where you could place an imaginary number and represent it visually? So the question now, why do we wait? Why do you have to wait till after calculus? Let me explain. Hold on, let me answer these questions, okay? One step at a time, okay? One step at a time. All right, so let's say I have a function, like something that you are familiar with, x squared, okay? F of x is x squared. If I asked you to graph that, everyone here is comfortable with graphing that, right? You go in and you graph it, and we all have a pretty good idea of like what's going on there, right? What you're actually doing here is you are doing to visualize this, right? To see this function, which is right here. You are putting the input here and the output here, aren't you? Like it came off a t-table, the in and the out. 0 went in, 0 came out. 1 went in, 1 went out. 2 went in, 4 went out. -2 went in, 4 went out. -1 went in, 1 went out, right? And so like what you're doing is each one of these points on here is one of those written as an ordered pair, yeah? So visualizing this function required 1 dimension for the input and 1 dimension for the output. Got it? For a total of 2 dimensions in order for you to visualize this function. But you were not allowed to plug imaginary numbers in here, were you? No, we hadn't even talked about them. We hadn't talked about complex numbers at all. So imagine now, if you will, that I go and I say, all right, let's look at that function f of x equals x squared, but this time I'm going to use z instead of x, and that's because it's standard in complex variables to use the letter z to represent a complex number so that you know that we're distinguishing it from x, which is what you do in a college algebra class. So now I'm saying, go ahead and plug anything you want into that. You can plug in 4, you can plug in I, you can plug in 3i, you can plug in 2 plus 5i, it does not matter. You're free to do whatever you like. All right? So let's try something in here. Let's do a t-table. Let's do the input and the output. Let's start with 0. 0 squared?
0.
Still 0. 1 squared? Still 1. Okay? 2? Still 4, right? But we're allowed to plug anything we want. So how about we plug in I?
So it'd be I squared.
What's I squared?
-1.
-1, right? Okay, what if we plugged in, I'll continue my table over here. What if we plugged in 1 plus I? That was that one right there, right?
Yeah. So
What if I plug that in? I'm going to square it, right? I'm going to square it. I wonder what that is. Let me do that over here.
yeah, that would be 0.
Well, hold on, let's see. Isn't that what it means to square something?
Yes.
1 here,
1.
1 here, I here,
I.
I squared, -1. These ones cancel, 2i. Where's 2i? Right there, right? Okay. So what's happening here is this. I took a complex number. It spit out a new complex number, didn't it? It did, right? So what if I ask us now to try and visualize this function? Let's try and visualize it. First, you need to be able to represent the input. How many dimensions do you need to represent the input? How many dimensions do you see here? 2, right? That's 1 plus I, right? So I need 2 dimensions to see what's going in. And then the output is also a complex number, which in order for me to visualize the output, I have to draw another 2-dimensional complex plane, don't I? So I need a total of how many dimensions to see this function? 2 for the in, 2 for the out. 4. Have fun. You can draw 4 dimensions for me? No, you're not going to. And that's why it's an advanced topic. We're working with functions you can't see anymore. It's in a dimensional space that you can't visualize. We love three-dimensional stuff. We love two-dimensional stuff because we can visualize it. But once you get past 3, it's a different ballgame. Yes?
Sorry, his question first and I'll ask.
Who asked?
Were you going to ask like the...
Oh, no, I have a couple of open questions, but you raised your hand.
No, I was wondering like, okay, so obviously you could square 1 plus I and
Yes.
get 2I. Is there
Yes.
a way that you could get the square root of 2I to get 1 plus I though? I don't see how that would work.
Square root of I is just.
No, like square root of 2I to get 1 plus I. Like how
Yes, I understand what you're saying.
Like how could you...
Because he's saying, look, how do I get from 4 back to 2? I take the square root, right? How do I get from here back to this? Right? Well, that's the definition, right? The square root of -1 is I. Yes? So your question would be, how do I get back to 1 plus I? I'd have to take the square root of this.
Oh, and then you would separate it.
You could separate, but hold on, that's still not going to...
Oh yeah, that's not going to do it.
Because the square root of I is not -1. Square root of -1 is -1. That's a very, very good question. And it's not easy for me to show you. Because you need something else. You need to be able to write... Complex numbers can be written in 2 forms. A plus bi, and then we have something called the Euler's form, which is a lot easier to work with. I'll show it to you. 2i is this. And now we're going way outside of what we need to do. That can be rewritten as e to the pi, 2e to the pi over 2i.
Whoa.
That is that number, written in a different form. And then you can take the square root of that, and that's easier to do,
I'm glad.
believe it or not. Okay? So I'm answering your question. There's a way to do it, but it's not something I can show you easily. All right? All right.
You're just going to let me know that my mind would be blown if you were to explain.
This looks complicated, right?
Yeah.
This is not that complicated. Okay. Gosh.
It's literally...
See, this is why I hate this section. I hate this section because I love complex numbers, but it's so difficult to hold myself back on this because there's so much here that we can get into.
I mean, this section looks kind of cool. But
So look, this number right here, I want to show you 2i, do you agree, is that number right there? Okay, all this says is you're going to be standing at the origin and you're going to walk 2 out, okay? I'm going to walk out 2. This right here tells you what angle you need to turn. So do y'all know what pi over 2 is? Do y'all know what pi is?
Well, yeah.
Angle-wise? As an angle, pi is 180 degrees. Okay? Pi over 2 is half of that, which is 90 degrees. So this means I need to walk out 2, but I needed to have turned 90 degrees first. So turn 90 degrees and then walk out 2, and that's where I am. Okay? Understand? Now, if I want to take the square root of that, which is what you were asking, pi over 2i, then what I can do is I can split this into root 2, and then I can go e to the pi over 2i square root, right? But isn't square root the same as raising to the 1/2? And when you take a power to a power, or something to a power, what do you do to these powers? Multiply. Multiply. Pi over 2 times 1/2 is pi over 4, isn't it? Pi over 4. So this is really going to turn into e to the pi over 4i, and this number out here is root 2. So if I want to take the square root of this number, what I need to do is walk out how far? Root 2, but I need to rotate by how much? Pi over 4. Pi over 4 is 45 degrees. So I'm going to rotate by 45 degrees, and I'm going to walk out root 2. And I promise you, if you walk out root 2, guess where you're going to be? 1, 1. You're going to be right here. Do you believe that that's root 2? How long is this side? This side? A squared plus b squared is c squared. That gets you there. That's 1 plus 1i.
that's actually really cool.
It is. It gets even cooler. The complex numbers are awesome.
But we're not allowed to have that cool stuff in here. We just have to have polynomials.
Well, yeah, you're not allowed. The problem is, again, what I said is the reason why we have to hold back is because you're not ready for four-dimensional things. You're not ready for that yet. Trust me, you're not ready for it, okay? You got to get a lot of other stuff out of the way first, but it gets pretty fascinating. So I will answer now the question about when this would become applicable, okay?
Theoretical physics?
Okay, my brother's an electrical engineer, okay? And a lot of times what we have to do in math problems is take a look at functions and imagine that your x values can go in both directions forever. So like, we've looked at polynomials where we have left and right behavior, right? And what we're saying is as x goes to infinity, negative infinity or infinity, like what's happening in both directions, right? And it can be very difficult to look at a function in both directions forever, because how do you actually go forever, right? It's impossible for you to go forever. But there is a workaround, okay? There is a workaround. And here's how it's done. Imagine this complex numbers. Imagine that set of complex numbers. Remember, it was a flat sheet of paper, wasn't it? Here's the real axis. Here's the imaginary, right? I'm just going to put that. That's that sheet of paper I just had up here. I'm just laying it down so it's in three-dimensional space now. Do you see it?
Yeah.
Okay, so if I'm going to move around the number line that we deal with in our lives, it's this one right here. If I want to go out this direction forever, in this direction forever, that becomes impossible for me to do sometimes, or very difficult for me to go both directions, yeah? Okay, I just happen to have something I can show you. Oh, what are the odds that it's actually open? Wow. Okay, so here's, I'm going to kill some lights. There. All right. So do you see that sheet? I did not intend on covering this. This is actually kind of amazing that that happens to be open. I wrote this code a few years ago just so I could demonstrate this if I wanted to. I'm going to have to get up here for a second. Let's say that I want to move along this line forever in both directions, right? Like that. Then what I can do is I can associate with every point on this line. What I do is I put this ball on top of this sheet of paper, okay? See this? It's like a sphere. And starting at the North Pole, I'm going to draw a line connecting that point and that point together. And when I do that, at some point I'm going to punch through the ball. Do you all agree with that? Yeah. I'm going to punch through right there. So this point right here now corresponds to that point on the sphere. Agreed? Okay. And I'm going to continue to do that for every single point on this line. And watch what happens.
Wait a minute. If you're on the North Pole, then technically you wouldn't have to punch through in the first place, because that's at the very apex of the sphere.
Yeah, hold on. Let me get my, I can do it from right here. Okay, so look, I'm going to move, I'm moving that point, watch. I'm moving that point. Where did the point that corresponds to it go? So for this point now corresponds to that point. Do you see that? And as I continue this, moving along that straight line, man, I did a pretty good job of drawing a straight line. That's not bad. This point now corresponds to this point. So do you see that this line, I'm turning it into this right here? Yes? Yeah. Okay, and then I continue to go and draw the rest. Now I do have some restrictions here because of the code. But do you agree that if I went out further and further and further, that this point would be higher up on that circle? Yes? Yes? Okay, what would infinity be? Where would infinity be on there? It wouldn't, right? It would be impossible?
Eventually, it would just...
Eventually, what's happening is this line's trying to get flatter and flatter and flatter. So couldn't I actually call infinity the North Pole? The North Pole would correspond to infinity.
Theoretically, I suppose.
Yeah.
Yes, right?
If it just keeps going.
Because if I'm anywhere on the line, right? If I'm anywhere on that line, aren't I somewhere on this circle? And it's getting closer and closer and closer to the North Pole the further I go out. If I could go to infinity, I would be at the North Pole, if I could.
And the same with
And the other direction is going to wrap us back around to that same point, isn't it? Mm-hmm. So the reason why I'm saying this is because if you have a problem in engineering or in physics where if you're stuck on a real number line, if that's all you know is the real number line, then you are going to have to go in both directions forever. But if you are aware of the complex variables and the complex functions, then you're no longer on a line that goes in both directions forever. You're actually on a circle. And it's much easier to do math on a circle than it is to do on a line that goes in both directions forever. So imagine if you could, you've ever watched like a 3D movie? What do you have to watch? The goggles, right? You watch a movie without your 3D goggles, it looks weird, right? You can kind of follow what's going on. Same thing with this. Look, all we have ever known in our lives is the real numbers. If you allow the complex numbers to come into play, you have these set of goggles that you can put on that will make things that are very difficult very easy a lot of times. I like to associate it to like a fish bowl, right? Or like a fish that lives in a pond. Here's a pond. There's the land. You've got a fish living in the pond. There's my fish. Okay? The fish is totally unaware of the fact that there is a cow out here, right? This fish thinks that this is the universe. And maybe that's all that matters to the fish, right?
So that pond is our real numbers?
The pond is the real numbers. You live in a pond. The real numbers are a pond. What you need to understand is that there is a larger group of numbers that your pond lives in, that your real numbers live in, that you need to have the whole picture to understand what you can do with it. And for a long time, they thought this was ridiculous. It made no sense. Like, throw it away, it doesn't make any sense. But it turns out later that they found out, you know what, no, we need to define this, and it's... They proved it by doing this. I can never get this. We know already that a parabola can either hit the x-axis never once or twice, right? And the formula for this, the quadratic formula, right, is negative b plus or minus the square root b squared minus 4ac all over 2a. In this case right here, what would happen in the quadratic formula is that what's underneath the root would be negative. If what's underneath the root is negative, this is what's happening. And that was okay. That's why people said, look, you're crazy to think that the square root of negative 1 needs to be defined because, look, geometrically it doesn't matter. But they came up with the formula for a cubic function. Okay? Now a cubic function looks like this. That's what a cubic function looks like, right? We have a quadratic formula for quadratic functions that gives us the x-intercepts. We actually do have a cubic function that gives us the x-intercepts of a cubic. We have one. It's ugly though. It's real ugly. You can Google it. Cubic equation, all right? It's nasty. But what they saw was that there are times when you use that formula where you get the square root of negative 1. Now, why is that profound? Let's see who here can make the ultimate connection. Here, the square root of negative 1, that corresponds to this. You're crazy. Who cares? But they saw over here they were getting square root of negative 1 also.
It's like, where do you put that?
Negative 1 correlates with the imaginary numbers?
Yes, but they were in the formula they were getting square root of negative 1. Over here, again, over here they were saying, look, I'm getting square root of negative 1, and all the person would come in and say is, yeah, but look at your graph. It's not hitting the x-axis, you idiot. Over here they were getting the same thing. They were getting square roots of negatives.
But it's a three-dimensional, so it's actually...
No. But
It's an odd degree.
it's odd degree, which means, exactly. Come on, I'm getting chills. Okay, you see it. It's odd degree, which means it has to do one of two things. Down on the right, or down on the left, up on the right, or the other way around. No matter what, it must do what? Cross the x-axis. There's no way around it.
Because the whole doesn't...
And that means the negative root had to have meaning. It had to have some meaning. And that's it. That's all it took. And once they had that, they said, look, we have to make it. This was a bad example because it didn't cross. But with a cubic, you cannot get around it. You can't sit there and say, oh, well, it doesn't cross. You're crazy. It does cross. So you better be able to define the square root of a negative number, or else you're never going to be able to deal with that. That make sense?
Holy crap.
Cubic equation?
Yeah.
Yeah. Okay, so there's a cubic equation. There's also one for fourth degree.
Yeah, like
And it's about a page and a half long for fourth. And if I'm not mistaken,
equation?
I believe that it has been proven that there is no equation for fifth degree and higher. So listen to what I'm saying there. I'm not saying that they have not found an equation. I'm saying they have proven it does not exist. That it is impossible to have an equation to find the x-intercepts of fifth degree polynomial functions or higher.
Well, that's because we can't see it in fourth dimension. Maybe if we could see it in higher dimensions, we could understand why.
Well, okay. Well, I've done a great job of eating up about 45 minutes of class.
I think staying on topic.
Okay. So,
So we're not gonna actually show this one test.
yeah, you know what? I think I'm going to give you on the test, I'm going to give you some advanced complex variable topics. How about that?
No, you're going to give us a problem where we have to use the key.
That's called a stereographic projection. For those of you who are interested, that's a stereographic projection, also known as a Riemann sum, a Riemann sphere. Riemann sphere. Okay, so hopefully I've convinced you that the reason we don't mess with complex numbers is because they take too many dimensions for us to be able to visualize. But the fundamental theorem of algebra says that we're guaranteed that we can, if we have a polynomial of degree n, then there are n factors, possibly repeated. Okay? Did I spell possibly right? That doesn't look right. Okay.
That looks right.
Okay.
Should be something we should be in there.
Possibly.
All right, so what we're saying is this.
We're in math class, we don't need to know spelling.
We ain't need to know no English as long as we got the numbers.
That's right, Billy Bob.
All right.
Did all these people that seem
There we go.
that are like mathematicians?
This is what this is saying. If you have a polynomial function of degree n, guys, if you have a polynomial function of degree n, there are n factors, some of them possibly repeated. So they call it the fundamental theorem of algebra because this is a fundamental theorem. It's guaranteeing you are always able to factor an n degree polynomial into n factors. So when we're sitting back here and we're saying this one right here, and we're saying, hey, I don't know how to factor that. That doesn't factor. This guarantees you can, but you have to be willing to put in complex numbers. And I believe, let's see if y'all can guess what it would be. Let's see. I want to know when it's 0, right? Let's see. Move that 4 over. And now take the square root on both sides. And you are taking the square root. So plus or minus square root of negative 4. Didn't we just do that a minute ago?
Yeah.
What did we say? It was 2i, but it's plus or minus 2i. So that means when I plug in 2i, I should get a 0. And when I plug in negative 2i, I should get a 0. So I'm going to do this and this. Do you agree that if I replace x with 2i, this is 0? Yes? If I replace x with negative 2i, this one is 0. Do you believe that these two multiply to be this?
Has to.
Let's see. We'll check it. FOIL. X times x, x squared. X times negative 2i. How about negative 2ix? Fair? Is that fair? How about this one? Plus 2ix. Those are going to cancel. And then be real careful on this one. What's positive 2 times negative 2? Negative 4 times I squared, which is negative 1.
And that is 4.
And that's positive 4, and now you're left with x squared plus 4, which is this. Understand? Unfortunately, I can't graph this for you over the complex numbers. So this does have roots. This does have x-intercepts. They just don't live on our real numbers. So like if I'm saying, hey, what are the x-intercepts of this function? You would say, oh, they're right there and right there. Those are them. But see, they don't live on the real numbers. Understand that? Now, if you change this to a minus, the two answers were positive and negative 2. Those would live on the real numbers. Okay? Now, let's look at something a little...
Unless it's a negative x squared negative 4.
Sorry, I actually did not hear a single thing you said because I was thinking about the next thing I was going to say.
I was saying if it's a negative x squared, because it's going to go down, then negative 4, then it's going to at the same time.
Yeah, then it would be back to imaginary because you're just putting a negative through. What about this one? What does the fundamental theorem of calculus tell us here?
There's 4 factors.
Actually, you know what? Let's change this. Let's make it minus. Yeah, this one's interesting. This one's really interesting.
There's supposed to be 4 factors.
There should be 4 factors, possibly repeated, right?
Yep.
Now, can you tell me, using difference of squares right now, what this should be that we know so far? X squared plus 1, x squared minus 1. Do you all follow that? Okay, this one goes even further, right? X squared minus 1 turns into what? X plus 1, x minus 1. Agreed? But what about this one, x squared plus 1? It doesn't factor over the real numbers, right? But over imaginary, it should break down to be 2 things. You know what they are? X plus I, x minus I. Exactly. And there are your 4. Can you draw those for me?
Well, 2 of them.
Oh, no, you can draw them. Watch. 1, negative 1, up 1, and down 1.
I think the only confusing thing, though, is to keep in mind that's not the y-axis we're doing.
That is not the y-axis. This is the complex plane. This is just visualizing the complex numbers. There's also something else about the complex numbers that make them even more complicated. When you have a real number line, 0, if you give me 2 numbers, right? So someone give me 2 numbers.
5 and 9.
5 and 9. 5 and 9. With real numbers, we have this thing called trichotomy, meaning that there's only, tri meaning 3, there's only 3 possibilities. Either 5 is smaller than 9, 5 is bigger than 9, or 5 is equal to 9. So you give me 2 numbers, it's only one of those 3 things, right? They're either equal, one's bigger than the other, or the other one's bigger than the other, right? 3 different things. Complex numbers do not have trichotomy. Because if I pick 2 numbers in here, like let's say I ask you to look at these 2. Let's look at this one, that's a complex number, and let's look at that one. Which one's bigger? Your question should be, what the hell do you mean by bigger? Because here bigger meant to the right, didn't it? And over here to the left is smaller. Here, what do we mean by bigger? And that causes a big problem because you don't have a natural order to these numbers, right? There's no natural order. There's a very natural order to this, isn't there? Move left to right. With complex number, there's no natural order. You lose trichotomy, and that creates a lot of issues. Some good, some bad. Okay. Curious how far I can push this. What if I change this to an 8? What would change if I change that to an 8? This would be 4. This would be 4 and 4, right?
I mean, you would probably end up with 4 ink factors, 4 which are I, and then 4.
What would this one break down to be? Well, we just did that problem, didn't we?
Yeah.
We just did that problem. So why don't we just do it all at one time? X plus I, x minus I. What else? X plus 1, x minus 1. So we have that, right?
So those are all going to be x squared.
Yeah.
4 down, 4 to go.
And now what about this one? What should that one break down to be? X squared plus I
Yeah.
x squared minus I.
Then can you break those down?
Then you can break each of those down. But then you have to start asking what's the,
Yeah.
yeah, what does the I break down to be? And this becomes a little more complicated.
Wouldn't that, I mean, the x squared minus I be x plus 1, x minus 1? Or no? Or no, x?
It would be root I. That's the problem. So this, do you see that we could start to potentially look into this? Let me show you where they are, okay? Do you agree that these answers right here are exactly these? Yes? So it's just the same here. Those other ones are going to lie on a circle, because all those points lie on a circle, right? And they will actually be these corners right here. They're all equally spaced around the circle. These are called roots of unity. Unity, roots of unity. So if I had x to the 16th minus 1, I would have 16 equally spaced dots going around the circle. Yes?
Is that basically what you were doing right there? The roots of unity with the sphere?
No, that's different. What I was doing there was I was trying to find a way to take a sheet of paper that extends in every direction forever and somehow turn it into something that's easier to work with. So I turned it into a sphere. That's what that is. So that's different.
So with the roots of unity, the maximum you could have is 360 degrees?
Oh, no, because you can have half a degree.
Oh,
Yeah. You can have x to any power, doesn't matter, but even power.
but they'll all end up in a circle.
It'll all be on the unit circle. Now, if you change that to a 2, x to the 8th minus 2, that's different. They won't lie on the circle anymore, but they will lie. They will be connected to each other.
So if it's even, then it ends up in the circle. But then
No,
what
no,
if it's odd?
no, no. If it's odd, you'll have 7 equally spaced. X cubed minus 1. What's the only answer we know of that for that one? What's the only solution to this that we know? 1, right? 1 cubed is 1 cubed minus 1? Yes? The other 2 are imaginary. And they live on a circle, okay, equally spaced. So how many degrees in a full circle? 360. So if I divide that up into 3 equal parts, how many degrees? 120. So here's 90 degrees, 120. One of them is here. The other one is here. Those are the other 2 imaginary solutions to this.
So, okay, so assuming that we could explain a fourth dimension, are these imaginary numbers on that fourth dimensional plane? If you
No. The imaginary numbers live in 2-dimensional space, okay? They live in 2-dimensional space. But to investigate functions of complex numbers, you would need 4 dimensions to visualize that. Yes? Understand? And I mean, the thing is, who cares about a point just sitting in space? We want to send it through a function. We want to know what happens with functions, right? All right, so one more thing on this section that I want to talk about. The complex factors of a polynomial and I'm going to put a star next to this because this is the one part of this that you'll be tested on. Okay, not on your next test, but on the following. The complex factors of a polynomial function always appear as what we call conjugate pairs. So here's what we mean by this. If A plus BI is a